Okay, thanks for invitation to be here. And it's my first time in Russia, so it's a pretty nice experience. And I hope I will come more often. And the talk that it's about two applications of recursion theory to set theory. Actually, I know there are not so many set theories in Russian, but actually it's a kind of application to a real analysis. So you will not feel it's abnormal. So okay. First, I need to review some recursion theory, and this is quite different than the previous talks about recursion theory. It's about higher recursion. The classical recursion theory, they investigate RE set, and all of them below zero jump. But high recursion, they may investigate the more sets like hyperarithmetic or even arbitrary Turing degrees. So, and yeah, and it can build some nice connection between. It's a boundary between recursion theory and set theory, and so we will not be surprised. Okay, good. Okay, it will not be surprised to find applications of recursion, high recursion theory to set theory, but this talk is maybe different. It's actually application to analysis, and we will see how to apply it. So, okay, let omega 1ck be the least non-recursive ordinal. A recursive ordinal is an ordinal can be presented by a recursive Y ordering over omega, over numbers. And then we can relativize this notion to say omega 1x for a real x, and to say omega 1x is the least non-x recursive ordinal. And Kleini's O, okay, we can uniformly enumerate these ordinal notations to the presentations, and it becomes Kleini's O. Kleini's O is a Pi 1 complete set. And the set of ordinal notation. Ordinal notation is a natural number which codes a recursive ordinal. And there is a uniform way to enumerate these notions. And this is called Kleini's O. And we use the norm to denote the ordinal is presented. And we also can push the Turing jump to be higher levels, like zero jumps is the halting problem, and then halting problem relative to halting problem is zero double jump, and then we have 0.3 jump, or even 0 to the omega, and go on. And for arbitrary recursive ordinal, we can define the alpha Turing jump, but beyond omega 1ck, then it makes no sense because the enumeration, even the enumeration is not recursive. So we can only work below omega 1ck to define the alpha Turing jump. And the hyperarithmetic real is a real recursive in some 0 to the alpha, the definition. So this is just a basic fact from high recursion theory. And there's a very beautiful theorem proved by Kleini, and it's an analog of Lusin's theorem. And Lusin proved if a set of reals is Borel, if only if it's analytic and co-analytic. But this Kleini proved a light phase version for this. So it proved a set of numbers is hyperarithmetic if only if it's delta 1 definable. So this is analog of set theory result in recursion theory. And because of this theory, and then Spector and Gandhi can prove this very nice result. A set of reals is pi 1 1 if there's a sigma 1 formula. Sigma formula in the set series language, such that A can be characterized as a recursive enumerable set over L omega 1x. L, okay. L is the constructible universe. Gödel is the constructible universe. So this theorem opens the door between recursion theory and the world, because there are so many mathematical statements. They are below the pi 1 levels. So then we can use recursion theory to study lots of mathematics, because it's just a recursive enumerable set. If set is pi 1, then it's just a recursive enumerable set. Then we can apply recursion theory to prove set theory result. Yeah. Okay, this is a very basic result in high recursion theory. So if A is a countable sigma 1 set, then every member of A is delta 1 1. If A is only one member, then it's considered sigma 1 singleton. Then of course it can be proved by there is direct proof by calculated the predicate calculated. It must be delta 1 1. But if countable is also true, and every member is delta 1 1. And actually, you can see that in a reverse way, if it has a member not delta 1 1, then A has a perfect subset. If A is sigma 1 and has a non-delta 1 1 member, then it must have a perfect subset. So it's called a regular property of sigma 1 sets, either countable or has a perfect subset. So continual hypothesis is true for sigma 1 sets. Okay, now let's go to randomness. And Marat's talk already mentioned Martin-Löf randomness. But here we investigate very high randomness. Okay, what is delta 1 1 randomness? It does not belong to any delta 1 1 null set, light phase delta 1 1 null set. And Sachs, he proved some basic result on high randomness in 1960s. And if R is delta 1 1 O random, delta 1 1 random relative to cleanest O, then omega 1 R equal to omega 1 CK. So it does not increase the well order. So if R is random enough, then it has no power. It does not increase the well order. And every sigma 1 null set is covered by a delta 1 1 null set. And why this is true? And we can prove it using recursion theory, because this is a bullet set theory result. Every analytic null set is covered by a Borel null set. But we can prove it use light phase version and then just relativize to both phases. Then we can get the full result in set theory. But we don't use set theory argument. We use recursion theory argument. So, okay, how to prove this using recursion theory? Because it's sigma 1 1. So we just look at the complement of A. So A is sigma 1 1. Then the complement is pi 1 1. Pi 1. Then it means you can enumerate it, because pi 1 is an RE set. It's an RE set. So if you see X enters the complement of A, then there will be some stage you can see it. And then you enumerate these reals into the complement of A. And if you want to, and you can prove this statement, the measure greater than P for a rational P is also a Pan1 statement, because if you know this greater than the module A greater than P, then at some stage finally you will find it, because you enumerate R minus A, because you enumerate reals into the complement of A. If it's module greater than P, then at some stage you will find it. So it's a Pan1. It's a Pan1 statement. And because this A is null, so this has module, full module. Say we just look at the interval, the 0, 1. And so then we just enumerate all the rationals like 1 minus 2 half, 1 minus 1 over 2 to 1 over 4, and 1 over 2 to n. And then finally we will find the module will greater than half, greater than this, and greater than this. And after omega stages, we will find that, okay, it's greater or equal to 1. But it's just omega stages, and it's effective. So this is still Pan1, but it's stopped at some stage. And at this stage, because it's bonded, it is bonded, because finally we can find this. It's not, we will not enumerate the infinite time, we just enumerate omega time. So then we finally at some stage we will stop it. If we stop it, then it becomes a Borel set. Because at this stage, we find the module 1. Of course, there are some, still maybe some reals not enter to the complement of A, but we don't care, because we already found that it's a module 1. And how, and what's the, and then we just look at the list reals, and the list set of reals is just a delta 1 set, because it's bonded. A delta 1 set is just a recursive set, because the Pan1 set is RE set. So if we can find the stage, and then we found all of these reals, either in, at the, up to this stage, either in A or not in A, then it means it's recursive, so it's delta 1. So then we can find, and up to this stage, it becomes a Borel set, a delta 1 set. So we have this result. So this is, this is the rough idea how to prove this using recursion theory, using Specht-Gandy theory. Okay. Okay, now let's go to the classical randomness. And this is very weird randomness notion called Kurz randomness. If it does not belong to any pi01 null set, X is random, Kurz random if it does not belong to any pi01 null set. And so it's not really a randomness notion, because every one generic or weakly one generic is a Kurz random. But it unifies genericity and randomness. And Joanna and Stefan, they proved a result. They observed this result. If X is called Wagner-Barger theorem. Such theorem may say it's similar because it's like product forcing theorem. If X is Kurz random and Y is X Kurz random, then the join of X O plus Y is also Kurz random. But the reverse is not true. And we have this result. For any real X and Turing and the real Y, Turing above X jump, X is X Kurz random, such that R Turing equivalent to Y. So that means for any X and Y is X jump, then you can, over this upcomb, you can always find a random real R Turing equivalent to some element over here. So for every element here, you can find that Kurz random such that they have Turing, it has Turing degree over here. So it's just these are all the results we need to prepare to prove analysis results. Okay. Okay, this is not sorry. This is very important result. So if A is an uncountable delta 1 set, then A ranges over a upcomb of Klinius O. That means for any X delta 1 above Klinius O, then it has then A has a member y such that y hyper-equivalent to x. So it ranges up cone of clean. So this is something, this is also very like Martin's theorem for Turing determinants. But to prove Turing determinants, we need a very strong set theory assumption. There are infinitely many power sets. But to prove this theorem, we just need some replacement. So, yeah. And it's, yeah, and it's a very strong statement. You just need uncountable delta one. Don't need to be cofinally range. So, okay, this is all the result we need. Okay, I promise. Okay, now let's look at analysis. So, a function, real function has a losing n property. It was introduced by losing, and if the maps are null set to null set, so maps all the null sets to null set. Because he introduced this notion to investigate which function can map measurable set to measurable set. It turns out to be this notion is critical. So a function has a losing n property if the maps are null set to null set. And there is a very natural recursion theory interpretation of this notion. So it just says, okay, what is the losing n property? For a continuous function, it has a losing n property. It just means it does not decrease randomness. So that means, okay, there's a way to formalize this notion. So we just observe this simple result if f is a recursive function. So, okay, let's explain this. A continuous function is just a recursive function. For recursion, continuous is exactly a recursion function relative to an ORC. So, a continuous function is just a recursive function.
This is for recursive function is losing property, this proposition.
No, oh yeah, right. Right. I mean, yeah, if f has a losing n property, then yeah, right. So, every continuous function is just a recursive function, and then relative to ORC. So we just need to look at the real recursive function, and then to prove general result, just simply relativize to an ORC. So, if f is a recursive function and has a losing property, and then for any x, any delta 1 x random real, the preimage only contains delta 1 x. So it means if the image is already delta 1 x random, then the preimage is already delta 1 x random. So it does not decrease randomness. It's a quite natural recursion theory interpretation. Using this interpretation, we can prove some result by they were proved by some analysis. Okay, let's look at it. So, it does not increase randomness. Yeah. Does not increase randomness. Right? And let's look at a classical theorem by Banach. And if f is a continuous function, has losing property n, then it has a property T2. What is T2? This means for almost every real, the preimage of R is countable. That was proved by Banach in 1927. And this result was significantly improved by some Russian mathematicians, because many Russian mathematicians claim the result. So if I know write down all the names, then maybe several pages. But I just say Russian school, and Loville is such series in France. They prove this result. If f has, they improved Banach's theorem, because Banach's theorem says that f is continuous and has losing property n, then it has property T2. Then they improved to continuous to be measurable. It just needs to be measurable and has losing property n, then it has property T2. So for almost every real R, the preimage of R is countable. Now, we prove this result using recursion theory argument. So, we just prove continuous case because for measurable case we can. It's also almost the same proof, but we need more notions. So we just prove for continuous function. So how to prove it? Because if f is continuous, then we just simply assume f is recursive. As I said before, there's no difference to recursion theory. A continuous function is a recursive function. So now suppose f is a recursive function has losing n property. Now let R to be delta 1, 1 all random real. How many such reals? Measure 1. So now let R be delta 1, 1 all random. So by the pre-result, so if R is in the image, then the preimage of R is also delta 1, 1 all random. Delta 1, 1 all random. So it means now suppose A, okay, suppose A equal to the preimage of R. Suppose it is uncountable if it's uncountable. Then what's the complexity of this set? Is a delta 1, 1 in R, because f is a recursive function. So this set is delta 1, 1 in R. And then we can relativize the Martin's result. If it's uncountable, then it ranges over upper cone of delta 1, 1 degrees. So A must range is upper cone of delta 1, 1 all degrees. But we know every real here by the previous result, and we know every real here is delta 1, 1 all random. And if it's delta 1, 1 all random, if x is delta 1, 1 all random, then omega 1x equal to omega 1 ck. Then we got a contradiction, because if the range of upper cone of hyper degrees, delta 1 degrees, then recursive order, the order can be arbitrarily long. Then we got a contradiction. So we prove it. That's quite a short proof. Right? It's quite a short proof. And to prove the full result, we just using a Borel function to approximate this measurable function, and then using more high recursion theory facts. And it's not long, but yeah, it's also quite short. So you prove it using recursion theory. It's quite a natural proof. And also we can look at some other properties, like let's say a function has a losing M property, if the maps null set to a countable set, then we can prove if f is a continuous function and has this property M, so it's just stronger than losing M property because it maps a null set to countable set. Then we can prove there is no non-trivial continuous function. So if f is a continuous function, has property M, then f is a constant function. And it also can be proved by recursion theory argument. This time we don't use randomness, we use genericity, covariant reals. So how to prove this? It's also quite short proof. So again, we assume this function is recursive, no difference. And so let G to be delta 1, 1 O OX. Okay, fix any real x. Fix any real x. And then if let G be delta 1 1 OX, then for minimum, so this is X, this is G. They form a minimum pair in the delta 1 1 degree. Minimum pair is just a pair of degrees. Everything below both of them must be delta 1 1. So they form minimum pair. And X cannot, okay, X must be covered by a delta 1 1 G nar set. This A, delta 1 1 G nar set. Cover X, or X is not random relative to G. Why? Because G is generic over X. It can predicate arbitrarily long bits of X, so X cannot be random. So it must be covered by delta 1 1 G set. Then it means the image of A must be countable. And the image of A is countable. It's countable, but this is a sigma 1 1 because A is delta 1 1 G. So this set is a sigma 1 1 in G. So it's countable. Then everything in this set must be hypersymmetric below G. So every real in F is hypersymmetric below G. But F is a recursive function. So Z recursive in X. But they form minimum pair. So Z must be delta 1 1. But this X is arbitrarily real. So it means the range of F must be countable. But the continuous function, if the range is countable, it must be constant. So we prove it. So this recursion theory proof. And we can, to prove the second result is by the same principle as before, and using, yeah. Okay, now, but there are some open problems left. So actually, we can prove for every measurable function has Luthian property, has T2, but we don't know whether this is true for arbitrary function. And but actually, we can prove it's consistent with GFC. This function has Luthian property, but for non-null set, the preimage is not countable. Actually, it can be proved under continuous hypothesis by a simple diagonalization argument. But we don't know whether it's a CFC theory. Because I know the Russian school, they are master on analysis. So maybe you can find an example using CFC. But what I can prove is just it's consistent. This is a counter example. But we don't know whether this can be proved by using CFC to construct such example. I don't know. And to prove it using CFC, and we can reduce it to a pure recursion theory question. So whether there is an uncountable idea of Turing degrees such that for any real X and for R, almost every real R is random relative to the idea generated by I union X. Random relative to an idea means random relative to element in this idea. Random means multi-lawful random or arbitrarily reasonable random notions. So we don't know. It's an open problem. But they both have positive answers on the CH actually. So, or on the V equal to L. The second one has. Okay. Module one set, yeah. So this is, okay, this is the first application of recursion theory to set theory. or analysis. Okay, let me talk about the second one. Well, this was another question asked by analysis. Given a collection A set of reals, we're using sigma A to denote the sigma algebra generated by A. So Borel set, it's a sigma algebra generated by open sets. And what is the Yodong measurable set? A set of reals, Yodong if the characteristic function is Riemann integrable. And we use J to denote the collection of J. Okay, now let's look at Johnson. He looked at sigma J, the sigma algebra generated by Jordan measurable set. And he characterized this sigma idea. He proved sigma J are exactly those Borel can be presented by a Borel set with a subset of F sigma null set. So it's a nice characterization of sigma J. But he asked a question. What's the relationship of sigma J with the analytic set? So it's certainly strictly about Borel set. But he doesn't know whether it contains analytic set. So, and this question also asked by several set series. For example, Arnold Miller set series in Wisconsin medicine. And then this question was answered by Maldin from North Texas. And he answered this question by showing Lake's analytic set, which cannot be generated by a Yodong measurable set. But his proof is quite set theory using well order of reals. But actually, we have quite a natural example. We don't need to construct it. There's quite a natural example which does not belong to sigma J. Okay. First, let's look at a thin set. A thin set is a set of reals has no perfect subset. And it can be proved by, I'm not sure this is out by recursion zero set series. And there is the largest pi 1 thin set is this x in or L omega 1x. So it cannot, so yeah, it's like something like a mass codes in L, all the mass codes in L. And this is, this is quite a natural pi 1 set. And we will use this to refute, to give example. But in quite a recursion theory. Okay. Now, first we prove a baby version. So suppose every real is constructible, then this set does not belong to sigma J. Of course, C cannot be, this result cannot be proved by GFC because C may be countable. It's consistent that C is countable. So we only know, so we need some satisfactory assumption. Every real is constructible, then C does not belong to this. Okay, why? It's a very interesting proof. And so, suppose every real is constructible. So if C can be presented by Borel set union some set X, which is a null set of F sigma null set. Suppose C equal to this and the union. Okay, because B is a Borel set, and it has no perfect subset. Why? Because C has no perfect subset. It's a Borel set, so it must be countable. It must be countable. So there's a bond, there's alpha, and every member in B must below this L alpha, because it's countable. So then all the other things must belong to this X. So this X has a very heavy burden, and he has to bear lots of things. but it's a subset of f sigma null set. So we can use a real x. And so it's just a light phase sigma 0x, sigma 0 2x null set. Then it means it belongs to sigma 0 2 x null set. That means every member in X is not X curves random. It cannot be X curves random. But we just need to find a real Z, which is a mask code in L, such that its Turing is not belong to L alpha, and greater or equal to X jump, Turing jump. Then we know there's a curves random, X curves random are Turing equivalent to Z. And also has this property because they are Turing equivalent. So it also has this property. We got a contradiction. Because this R cannot belong to sigma 0 2x because it's random relative to x, curves random relative to x. So we prove it. So it's a recursion theory proof. And of course, this we need some additional statistical assumption. But as I said, to prove both phase version, we just need to relativize this proof. So we can prove it actually using CFC. And look at this set. This is an example does not belong to sigma j. Because I don't have much time. So yeah, I just tell the idea. So it's a relativized the proof. And so if it can be presented by the same way, and then you can just look at the complexity of this F sigma null set and this Borel set, and can relativize to X. So the Borel set becomes delta 1 1 X set. This X becomes sigma 0 2 X null set, a subset of sigma 0 2 null set. Then we can apply the previous argument to find member does not belong to either of these. So it's quite a recursion there. So Maldin has after he solved this question, then he asked more questions, more general questions. So a sigma idea is idea which is closed on the countable union. So like null sets, the collection of null sets is sigma idea. Is closed on the countable union, right? So for what sigma idea, we can derive similar result. That means if we replace this F sigma idea to null sets to be other sigma ideas, well, then what we can prove? Sigma idea is sigma idea. An element of sigma idea means a very small set. So if it can be presented in this way, that means this set is kind of Borel set, modular, very small set. So he wants to know, for what sigma ideas we can prove that every sigma 1 set can be approximated by Borel set. But first we want the sigma idea to be simple. Because if the sigma idea is not simple, it's not definable, then it makes no sense to investigate. So we just look at the Borel, the sigma idea generated by Borel sets. So a sigma idea is Borel generated for every member X in I. There's a superset Y in I, include X. And we can prove this. This was also investigated by Kakris and Solesky. They proved some result under PD, projective determinants, but we are recursion series, and we want to know whether there's a characterization under V equal to L. And then we prove this. So a sigma 1 1 set can be approximated by I. It's a pure recursion theory question. just this element in I, which ranges up cone of hyper degrees or delta 1 degrees. And for the boldface analytic, then you just need to relativize this statement. So this is what we proved. And so it becomes a success theory question becomes a recursion theory question. And of course, you can apply this result to answer Johnson's question because it's a more general result. Thanks.